Thank you so much. It's a pleasure to be here, and it's so nice to see this room like full of young people. It's fantastic. So I hope you're enjoying the school, and I hope you enjoy hearing a bit about black holes and gravitational waves for the next half an hour. I think you should feel free to ask questions during the talk. I prepare some material, but I'm really looking to hear what you want to learn about. So the main topic of today would be what can we learn about cosmology from the binary black holes, and in particular, I'm thinking about those which are the farthest that we can detect. And whenever you think about exploring the most distant universe, this is always powered by gravitational lensing. So we know that when gravity, it's always attractive and light falls into the gravitational potentials. So any cosmic messenger is actually also gonna feel this intervening matter. And this means that if you have faraway sources, some of them might be actually passed so close to a galaxy that, oh wow, this is very fancy, that you may have multiple images of the same original source. And this, of course, allows you to observe signals which otherwise would be too faint to observe. But overall, as well, when we think of just any source in the universe, they are all affected by gravity, and they are all affected by weak lensing. And this means that if you want to do cosmology, precision cosmology, you always need to include these small effects from lensing. When you think about gravitational lensing, this is something that only becomes more probable as you go to farther away, to farther sources. And one way of quantifying this is in terms of the optical depth that tells you the probability that you have a signal that is going to suffer these effects of gravitational lensing. What you see is that when you have signals which are below redshifts of 1, then the probability of lensing is very small, but then it rises quickly when you pass this horizon. What you see here as well is that you never reach numbers larger than 1%. So this means that strong gravitational lensing is always a rare effect, but when you have large catalogs, as we will have in gravitational waves, this is something that will be important. And when I say that all sources in the universe are lens, this is a way to represent that. So these signals, when they pass close to an inhomogeneous structure in the universe, they can get magnified, so their intensity can increase. And then this depends on the source, of the lens, but also depends on how close the messenger is passing by. But overall, all signals are magnified, even if it's for a little bit, and some of them may be highly magnified. So what you are seeing in this plot is the probability distribution of magnifications for signals at different redshifts. So this is blue is redshift 1, orange 3, green is 10. So what you see here is that magnification of 1 would mean essentially that you are not changing your signal. If you have magnifications which are larger than 1, you are magnifying it. If you have lower, you are making it dimmer. So what you see is that when you are at low redshifts, this distribution peaks narrowly around 1. So this means that the most effect that you have is typically weak lensing with some small tail of strongly lensed events. But then as you go to higher redshifts, the effect of weak lensing becomes more important, and also the tail, the probability of having highly magnified events in a strong lensing also becomes relevant. So this is another way of quantifying a bit more this statement that I was saying. Now, when we think of gravitational waves in particular, I want to argue that these are actually really, really unique sources to probe the cosmic structures. And this is because mainly of these 4 reasons. The first one, which is, maybe it's not so special, but it's important, is that these binaries that we are merging with gravitational waves, they are merging at cosmological distances. So we are detecting binary black holes that merge a few billion years back on time. But more importantly, and I think this is very different to many other electromagnetic transients, from gravitational waves, we do understand what is the shape of the signal from first principles, because we can solve numerical relativity, evolve two black holes, and we get a waveform. And this is very important because this allows us to identify these signals and also to see the effects of possible distortions in these waveforms. Could be hints of new physics, or could be hints of new effects such as gravitational lensing. But even more importantly is that these gravitational waves, as they travel through the universe, actually they are only affected by gravity. They are not obscured by the center of galaxies. They don't interact with or any other medium. So gravitational waves, after they have been emitted by a source, they would only be changed if they feel a gravitational lensing. And finally, something which is also quite unique is that the wavelength of gravitational wave sources are actually of astrophysical sizes. And that's because the wavelength comes from the orbital motion, orbital separation of the binaries, and that's of astrophysical scale, because at most you can have wavelengths which are of the size of the black holes themselves. One way that I like to represent why the cosmological reach of the current observations is by plotting the distribution of binary black hole mergers as a function of cosmic time. So here the radial component is showing us that we are at the middle, 13.8 billion years after the Big Bang, and then the radial component brings us back on time. And what you see, each of these dots is just simulated data for some astrophysical population of stellar mass binary black holes that have some distribution across redshift. So what is remarkable is that already now we are reaching a few billion years back on time, but with the current detectors, just in the next observing runs, we are going to be able to really reach 10 billion years back on time. And with next generation of detectors, the green line, we are going to essentially see all binary black holes that have merged in the history of the universe. And this is important when you think in terms of cosmology as well, because the universe has changed a lot. Of course, we are now in a period dominated by dark energy, but as you look back on time, dark matter takes a more predominant role, and that's something that potentially could be measured with gravitational waves. Gravitational waves are, by the way, a reality, and we have already observed, and we have catalogs with 100 events. This is what we have from the first 3 observing runs. But what actually I think is more exciting to all of you is that we are actually taking data now. So if you scan this QR code, this will bring you to this website where you can get alerts in your phone every time that there is a merger in the universe. And that's important, of course, for the question as well of multi-messenger. If you look at what we have seen so far in the 4th observing run, we have already more than 200 candidates. So we have the 100 from the first 3 observing runs, 200 more here. So yeah, I think it's pretty exciting how fast we are evolving. And also you should be aware that there will be a lot of papers coming up this summer. So check the archive, because I think there's going to be a lot of results coming up. But of course, we like the present, but we are really motivated by the future. And that's because when you think of what we are doing now in terms of number of detections or in terms of how far you can detect these signals, we are really at the beginning. So this is just to quantify a bit more the previous diagram. So here you have on the left the number of events as a function of time. These are the 100 detections that we have seen so far. And this is what I was projecting for the 4th observing run. And here on the right, you have how far you can detect gravitational waves for different masses. And that's because depending on the mass of the binary, you can see if it's more massive, you can see the amplitude is larger, so you can see it farther away. But then if it's too massive, then the frequency goes to very low values, and then it goes out of our detection band. So that's why you have this shape. This is just describing the sensitivity of our detectors. But when you put into these plots what's coming next, you see that first of all, we are moving on the left from a regime of hundreds of events per year to thousands of events per year, tens of thousands of events per year, hundreds of thousands of events per year. So that, of course, changes a lot what the kind of science that you can do, because it's not only that you are looking at individual events, but you can do a statistical analysis of a lot of sources. And then what I was showing before of detecting all sources within cosmic history is this green line here, where you see that essentially you can go for some mass ranges to up to redshift of 100. And besides all of this is for ground-based detectors. There is also LISA, which is a planned space mission that will detect gravitational wave sources at much lower frequencies in the millihertz. So that will allow to observe many sources in the galaxy, which are very interesting, these galactic binaries, but also observe these supermassive black hole binaries that merge at really high redshifts. So this is also, of course, these mergers and this instrument will be really revolutionary in terms of gravitational wave astronomy. And this is a mission that has already been approved and is going to be operating. It's going to be flying in 2034. So yeah, in the next decade we should have a lot of exciting data. So I know this is a school, so I wanted to add some maybe some more math about how you study gravitational lensing. But then, of course, because it's only 20 minutes, I'm just going to flash this. But let me highlight that we have some lecture notes from the course that we are giving here at the Niels Bohr. So all the details can be found there. But essentially, what you want to do when you want to solve the propagation of gravitational waves in the universe, you want to solve Einstein field equations in the linear regime. So you want to have small perturbations, but then allow for your background to have some curvature. This equation might seem easy, but it's actually very difficult to solve in general. So there is a lot of work to really make this into something which is digestible. But what we want to do in the context of lensing is we want to make a mapping between the source and the observer through the lens. So we have these three elements which are relevant. And what we are going to do is we are going to take some simplifying assumptions about the lens so that we can simplify this equation. In particular, what we are going to assume is that these signals, they pass close to the lens, but actually the effects of gravity, even if they can produce multiple images, they are never going to be in the really strong field regime of general relativity. So this is what I'm highlighting here as weak gravity. And then we are going to also assume that the source and the observer are very far away and that the lens is small compared to the distances. So that's very nice because effectively reduces the problem, which is a 3D problem of solving the propagation, into a 2D problem because you can consider your lens as just being in a thin lens plane. When you take these two approximations, you bring them back to the previous equation, you can move to Fourier space, and then you get something like this, in which your lens signal is going to be your original signal times some amplification function. This function is an integral that takes into account all the possible time delays that you could have from the different paths from the source to the observer. So this is, if you want, very similar to what is done in quantum mechanics for solving the path integral. In general, this is also a complicated integral to solve, but if you have simple enough lenses, you can find analytical results. So in particular, if you have a lens which you just make as a point mass. Then you can solve this integral analytically, and you can get some expression. What is important here to note is that this function depends on the frequency, and it's going here in this is multiplying your original signal. So what this means is that lensing has the potential to change the frequency evolution of your gravitational waves. So lensing can change how the gravitational waves look, and that then you can go and try to look for these distortions. But not in all the cases you are going to have these. So in this, by the way, these distortions come from the fact that you can have produce multiple images that they are interfering and diffracting with each other. But it's not always that you're going to be in that regime. And in particular, if your lens is very big, then typically you can simplify a lot the integral because the time delays times the frequency are really large numbers. And then your amplification function simplifies to a sum of different images, each of them with a different magnification, time delay, and phase. This phase shift is actually important because it tells us the type of image that you have. And maybe the best way of understanding this is by looking at pictures. So if you have this dinosaur that is being lensed here, if you have an image of type 1, what you would be is essentially just magnifying the signal, but you would not be changing the orientation. If you have an image of type 2, what is going to happen is that you're flipping the image over this symmetry axis. And if you have images of type 3, you have flipped the signal twice. So this flipping of images is encoded actually in this phase, which is something actually with gravitational wave we have some sensitivity to. So in general, to summarize this part, we are doing a mapping between the source and the detector, and then we want to see the possibilities that could happen to this signal. And then if the lens is very big, what's going to happen is that the signal can produce multiple images. So then what you need to do is you need to go to your catalogs of gravitational waves and try to find signals that have similar properties. But there is also the possibility that if these lenses are smaller, and in particular, if the size of the lens is comparable to the wavelength of the gravitational wave, then you can be in this regime in which you need to solve this diffraction integral, and you can have your signal being highly distorted. So these are the main two regimes of gravitational lensing, and I'm just going to flash a few aspects that gravitational lensing provides for gravitational wave astronomy. And the first of all is that when you, and perhaps this is the most obvious, but it's important to remember, is that when you have lens signals, you are automatically expanding your horizons. So this is the plot that we had before, where I was showing the different horizon distance for different detectors. But even if we have our current sensitivity, if we have signals that were magnified by a magnification of 10, this would be equivalent to having detectors from the next observing run. And if it were to be magnified by signal by 100, then you would even go to next generation detectors. So this is maybe to emphasize a bit more that gravitational lensing is a portal to observe further distances. And this is interesting because you could think that you could discover new populations of black holes that you couldn't otherwise observe if it were because of lensing. So to represent this, here I have two toy population. One that is motivated to be from black holes that are formed from stars, which are in the field of a galaxy. And these, for those, we expect that the merger rate of these binaries as a function of redshift should have a peak of around a redshift of 2. That's because you need to form the stars, and then the stars need to form the black holes, and then you need to form binaries. So it takes some time through the history of the universe to really be able to have these binary black holes. But there are other formation mechanisms. So one could have black holes that form directly from the collapse of like a population 3 stars, and those could be produced at much higher redshifts. So that's quite interesting because if you look at these populations, and if you look at our current sensitivity, for example, for binaries in the field, we expect hundreds of thousands of those to merge every year in the universe. And then 100 of those per year would be lens. And then with detectors in the with current detectors at the same sensitivity, you could get about 1,500 events per year, and a few of them would be lens. But what is exciting is that you could also have this potential population that could be very large. Here, I'm just making some numbers to make it detectable, but you could have as much as 35,000 mergers per year. And that, because these signals are so far away, would lead to 0 detections in the next observing run, except if some of them were to be lens. So the only way to access in the near future these populations of potential populations of high redshift binary black holes would be through lensing. Yes?
Number of sources that will be lensed.
Yeah, so the number of sources that is lensed comes essentially is you are combining this merger rate with the probability of lensing, which was this optical depth that I was showing at the beginning. And that, of course, has some assumptions about what is the distribution of lenses, but you can compute it that way.
But is the data of the distribution of sources taken from some other sort, like the all-sky surveys, or is it?
Yes, so from for the distribution of lenses, we use what we know from galaxy surveys. For example, like we have a very good modeling of galaxies as lenses, and we know that those can be modeled with sector function. And there are more details, but from that data sets, I mean, you can create models that then you can use for this. But let me emphasize, I mean, that these populations of binary black holes, this is just a toy example, but I think it gives you the hint that it's a possibility that you can reach through lensing to discover these new sources. Okay, and then I think the other important thing that it relates to the other regime is that because you can have distortions in your waveform when the gravitational wave is comparable to the size of the lens, this is a way of actually probing small scale structures. So if you think of current signals, you would be mostly into probing lenses with masses of hundreds to thousands to tens of thousands of solar masses. So this means with current detectors, we can probe the existence of compact objects or intermediate mass black holes if you want, or primordial black holes if you want, that could be producing these distortions in the gravitational waves. But then if you think of LISA, then LISA actually would be a way of probing actually subhalos, because the scale of the wavelength of supermassive black holes is comparable to the size of lenses of 10 to the 8 solar masses. So depending on the source, you can reach different regimes. And I know I'm reaching close to the end, but I think something which we have been working here, which I think is very exciting as well, is that when you are approaching when you're in a strong lensing, there are certain regimes where you are close to these caustic regions, which are the ones that define the maximum magnification, where actually there are universal predictions for the amplifications and time delays and type of images that you have. So actually, it's a really well-defined and universal behavior that you can go and look into the data. In particular, if you are in the really, really, really high magnification regime, at some point what happens is that your images actually start to blend with each other, and you could have also overlapping signals and even diffraction patterns. before I end, I think it's important to mention that we are currently very actively looking for these signatures of lensing in our data sets. However, we have found no evidence yet, neither of repeated chirps of the same signal or evidence for distorted signals in the data. With this knowledge that we have not observed lensing, we can still make some learnings about the emergence rate of black holes at high redshift, and we can also constrain the population of the existence of compact objects that would lead to lensing. But something which is important is that when we look for the signals, actually we are using templates. So we are using models for gravitational waves, which are actually based on signals that have not suffered lensing. So something that my student, was finding is that if you actually have signals that have been highly distorted due to lensing, actually with our current searches, some of them might be missed. So I think we need to have a grain of salt in the results we have, but I think that's interesting. And then I think I'm just gonna jump back to the conclusion to say that gravitational waves are really precious cosmological probes because they are well understood and because they travel through the universe unaltered except for gravitational lensing. I've tried to argue that the gravitational lensing could be a portal to learn about new populations of black holes at high redshift, but also to learn about the small scale structures in the universe in a way which I think is quite unique. And of course, you should all be excited because this field is really growing, and I think there is a lot of discoveries to come. Thank you very much for your attention.
Thank you, Jose. Very envious from the point of view of neutrino astronomy, how many discoveries you made in the recent time. Are there questions? Yeah. Start here.
Thanks for the nice talk. Actually, I have two questions. So the first one is basically like you mentioned, so the gravitational lensing, when the size of the lens is sort of comparable to the wavelength, so you are basically, you diffract it and you phase shift it, and the amplification is frequency dependent.
Yes.
So basically if you have binary neutron stars, then there is the tidal deformability signal also is phase shifted. So how are we gonna say that this is tidal deformation or this is lensing? Like how are we gonna differentiate?
Yeah, that's a really excellent question, and it touches on the point that if you are trying to find this new effect, you need to distinguish from other possible effects on the source. I think for the tidal deformability in particular for binary neutron stars, I don't think this will be a big degeneracy because it's an effect that mostly peaks around the merger, and then binary neutron stars are long signals, so lensing in this regime would produce effects, I think, much bigger earlier in the spiral. However, I think there is a very important parameter, which is the precession that I didn't mention, but which is that your black holes can be spinning in different directions, and then that can make the whole binary to precess, and actually that can lead to modulations of the waveform that actually resemble some of the effects of lensing. So there are degeneracies there that one needs to overcome. I think, for example, if you have signals which are close to the caustics I was mentioning, and you have concrete predictions for the magnifications of the images that are interfering with each other, I think this is a way in which one could break some of these degeneracies. But in general, I think it's very important that you need to take that into account.
Okay, thanks. My second question is basically, yeah, okay. So the second question is basically regarding the dark matter detection.
Yes.
So let's say your dark matter structure is has the same size as your basically we are in wave regime.
Yeah.
So how are we gonna so let's say you detect some signature of these modulations and say that okay, this is some kind of lensing, and you fit some template, and how do we basically say that okay, this is this dark matter model? So what should be the approach to sort of disentangle which model it is?
Yeah, that's another very good question. So depending on the density profile of the lens, the diffraction integral that I was showing is solved in a different way. So you can have some differences in the distortions that you predict. So that's a potential way of doing it. That being said, it could be that different dark matter models like produce the same type of distortions. But I think what would be something that one can probe more at the basic level is, for example, if you have comparisons between warmer and colder dark matter. If there is warmer dark matter, you have less substructure. So for example, so that will mean that you would expect less of these lens events in this regime. Or if, for example, you were to have halos with more concentration, then that will also increase. They will go in the opposite effect. So yeah, there are the generacies, but I think one can get some handle into different predictions, and yeah, in terms of the abundance of these signals, and also in terms of the different profiles.
Okay, thank you.
You follow up?
Yeah, please.
But you're actually assuming a matter profile, right, for these lensings, so that this matter profile must be assuming one dark matter model.
Exactly. Yes.
So you try difference, and the one that suits the most is something that you.
Yeah, that would be eventually, I think, the approach. Yeah. I think
Okay.
what is also, more at the basic level, I see you're asking very advanced questions, but maybe I should have said that I think one of the exciting things is that with electromagnetic observations, it's really difficult to go to halos which are smaller than 10 to the 8, 10 to the 9. And that's because that's at the regime in which the angular separation makes the different images overlap. So then you cannot distinguish that. And this leads to small effects in the images. But with gravitational waves, you can go lower in mass. And I think that's the key point, that we are sensitive to time delays down to the millisecond. So I think that's what is powerful. Of course, we don't know what, maybe it's just like cold dark matter, and in that case, maybe we don't have that many, but I think it's good to explore. Yeah.
Super exciting. Thank you.
Thanks. Right now at the moment for the LVK collaboration, when you claim that you detect a binary system, do you know the information of the ratio between the mass in that binary system, or do you have some kind of assumption or limit in that binary?
The ratio of the masses?
Yes, for example, layer 2.
Yes, absolutely. So we detect the masses of the binary. Yes.
But then the ratio between, like, for example, like M1 and M2, like the the binary neutron star, binary black hole. So
yeah, so we actually, so the quantity that we best measure is the shear mass, which is a combination of both masses. But we also have measured independently each of the masses, and from that you can get the ratio.
Okay.
Yes.
Okay. I had one quick question. So
Yes.
when you are talking about this magnification,
Yes.
does this also go the other way, that you demagnify and
Yes.
you're losing information?
So you could have that, and actually when you have multiple images, some of them are demagnified. So that's actually makes it more difficult to detect. But then what we do is that we have also searches that we call sub-threshold searches, that if, for example, we have a pair of events that we think are lens, then we know more or less the properties of the signal, and then we can improve our search strategies so that we can look only in the data to signals with the same property, and this allows you to go to detect things with lower signal to noise. So, but of course, if you demagnify a lot, then you could lose that. But always one of the images is magnified at least, And typically 2 of them are magnified.
Okay, I don't see any further question. Let's thank Jose again.
Yeah, thank you so much.
Thank you so much.